Have you played Trysting Tree in Corvallis, Oregon? It is the home course for the Oregon State University golf teams, and it is a great test of golf. The course is long with generous fairways, which means you can score well, yet they will grow the rough extra high for the NCAA events. If you think about it, Tiger and Phil both played Trysting Tree back in the day. Welcome back to another episode of Paula Marie Club's Ask Dr. Paul. Today we're going to highlight Thermoset Plastics. So when your boss talks about coefficient of linear thermal expansion, or CLTE, of epoxy molding compounds, what do you need to know? Epoxies have a lot going on with their unique chemistry, including condensation polymerization of ring opening epoxides and alcohols to build molecular weight, and benzene rings for high modulus and temperature capabilities, and ether structures for toughness, and alcohols giving polarity for attach and wettability. Epoxy molding compounds, or EMCs, can be cross-linked with amines and are highly filled thermoset plastics. How filled, you might ask? How about filled like a University of Michigan football game against their main rival OSU? And this time I mean the Ohio State University. Remember, thermoset plastics like EMC typically have better chemical and temperature resistance than plastics, and EMCs specialize in providing extremely low and favorable CLTE values, which approach those of glass and metals. EMCs use a handful of fillers such as calcium carbonate, aluminum oxide, mica, silver, and gold, yet 90% silica-filled epoxy works wonders, and that EMC's thermal mechanical analysis, or TMA plot, is shown on your screen. That's the red plot of dimensional change versus temperature. The light blue line represents the data below TG and gives a CLTE value of 10 parts per million per degree C from measuring a sample's length and the change in length from a given temperature range. Units are micrometers, or microns per meter per degree C, which we will call parts per million per degree C. This means when you heat this EMC below its TG, say up to 150 C, it will only move 10 microns per meter per degree C, or 10 ppm per degree C, which approaches silicon, say for microchips, which might move 2 to 3 ppm per degree C. Above TG, which is the orange vertical line, the plot shows a slope increase as shown with the dark blue line, and the CLTE above TG is calculated at 40 ppm per degree C, again by knowing the test sample length and the change in length from the corresponding test temperature range. Now we know TMA evaluates polymer expansion with heat and determines TG and the CLTEs above and below TG. So how do we create EMCs with low and thus favorable CLTE values? Silicon chips have CLTE values about 2 to 3 ppm per degree C, and that gives us a starting CLTE target. You can see that unfilled epoxy, a common adhesive product, has CLTE values of 50 to 100 ppm per degree C. But if we fill epoxy with silica at a high level, say 90%, it makes sense that the CLTE will decrease and the modulus will increase once we see the silica CLTE value of 0.5 to 1 ppm per degree C and a modulus value of 70 gigapascals. The table shows EMC CLTE values below TG of 10 ppm per degree C, while copper has a CLTE value of 17 ppm per degree C. That means you can stack EMC next to silicon and even copper, and they will respond similarly to heat. And that is important in the automotive, cell phone, computer, and camera industries. Knowing that EMC is a highly filled epoxy with CLTE values between silicon and many metals, that's working knowledge. Remember to like, subscribe, turn on notification, and even share if you appreciate the content. You can visit our website to learn more about our upcoming Rigid Polymers course. I'm Paul Nash for Paula Marie Club's Ask Dr. Paul. Thanks for watching.